Thank you. Very good morning, everyone in the room, and also to the audience in the online streaming event. So very good morning or very good afternoon or evening, wherever you are. First of all, I want to thank HPC Now for having us here in this edition. Again, it's, I believe, already 8 years in a row that we are Adamantium sponsors of this event. Personally, I'm very proud to be here to be able to share with you what we see in the current technology landscape. And I also received a lot of feedback from you guys on your needs and how we can do things better. Well, today I'm not going to speak about very glamorous things such as quantum computing or not as sophisticated as container orchestration that our friends were explaining yesterday. Today I'm going to speak more about hardware and an approach that that is intended to be created for an easy life for you guys as sysadmins or designers at some point in time. Okay, so I will speak about the Lenovo SharedIO. It's a different approach on how we connect machines to a low latency network. That's it. It's pure hardware. So having said this, okay. So later today, I'm really looking forward to listening what our friends from Corellis Networks have to say. So unfortunately, some years ago, the development of the OmniPath interconnect suffered a hiccup, and now while we are recovering, we need to see where we are as of today regarding low latency networks for our compute clusters. So Infiniband as the de facto standard, where are we today? Today, generation after generation of Infiniband technology, starting with SDR at 8 gigabit per second, we have come up to 400 gigabit per second that Infiniband NDR is providing us. Currently in use, what I see in my customers and in many places is that, and maybe Cornelis may agree to this, that in many cases, 100 gigabit per second as the data rate for a single compute node is more than enough for the workloads, and we will see later a very paradigmatic example of that, of a large supercomputer that is working at 100 gigabit per second per compute node. So as many customers still using EDR interconnect, also many of you are familiar with HDR at 200 gigabit per second. You are implementing networks of HDR, maybe using the HDR 100 feature. I mean, you can use just the bandwidth. And we are starting implementing NDR today. Well, Infiniband, this logo in on the left lower side is not the official one of Infiniband, but it's cool enough, so I needed to put it there, sorry. Comparing what we are currently selling today, HDR and NDR, also for backwards compatibility with EDR. You know that generation after generation, every Infiniband technology is backwards compatible with 2 generations prior to it. So today, HDR based on so-called NVIDIA quantum architecture and NDR based on quantum 2 architecture. I needed to say this because I don't want to be the only one not speaking about quantum in these days, but this is, I mean, I need to stop here because I know nothing else about quantum. Now, sorry, excuse the bad joke. So now talking about the features of HDR and NDR, you are already familiar maybe with HDR. Each one you switch has 40 QSFP ports rated at 200 gigabit per second. And with the use of the splitter cables, we can divide this bandwidth into 2 and have connections to host up at 100 gigabit per second. So nothing, well, some improvement in latency, but no improvement over ADR at 100 gigabit. So that's it. But we can connect more hosts to a single switch. With NDR, it happens that the one you switch, and maybe you are not that familiar as with HDR. With NDR, every one you switch has 32 ports, but they are actually 32 twin ports, meaning that each of the physical connectors has 2 ports, 2 NDR ports at 400 gigabit per second, or 800 gigabit per single port, if you like. But they are actually 2 ports. So the first improvement, also not only the bandwidth, but the higher radix, 64 ports against 40. And with the use of splitter cables, we can use also the NDR 200 feature. And we can have up to 128 NDR 200 endpoints at 200 gigabit per second per single switch. This is already a very nice improvement. Of course, as they are twin ports, so we always need to use splitter cables with this NDR switch. All right, let's go for it. So, well, it would look like with NDR, you can only get 200 gigabit, and this is what it is. I mean, you have 200 gigabit, or you have nothing. But let's see how we can do lower bandwidth for NDR as well, in order to be able to connect more endpoints. So first of all, I need to explain, well, I don't know if I need to, but I want to explain NVIDIA Socket Direct. NVIDIA Socket Direct technology is an approach developed by NVIDIA, formerly Mellanox. So in order to solve a problem of having one adapter, one Infiniband adapter, PCI by 16, connected to a single CPU, which is what happens in most cases. So one of the CPUs in your compute node, if you are having a dual socket compute node, one of the CPUs, whenever needs to talk to the network, to the outside world, needs to send a packet using the other CPU with a subsequent overhead and additional latency. So with the Socket Direct, what it does is it splits the 16 lanes of PCI Express into 2 sets of 8 PCI lanes, and then connects each of the subsets to each CPU. So each CPU is talking directly to the network without the need of talking first to the other CPU and then send the packet. So that solves the problem. Of course, the trade-off is that you lose half the bandwidth in each connection. But as we have said, sometimes that's not really a problem because you don't need so much bandwidth for each connection. So physically, we are using a regular. It's almost a regular Infiniband adapter with I would say an auxiliary card or a slate card that is connected to the master one with the use of a cable that is doing this split. All right. What we have done in Lenovo is take another approach, leveraging this capability, and instead of bifurcating the PCI lanes between the 2 CPUs in a single node, we are bifurcating the PCI lanes between 2 nodes. So with one single connection, we are providing connectivity to a couple of nodes. Every 2 nodes are using one single connection, which in the case of NDR 200 is very convenient if we want to have only 100 gigabit per second in each node. We do this with HDR. With HDR, it's already in the market. It was developed by NVIDIA. We are using it. There's nothing very fancy, and not even with the NDR approach. So with the NDR approach, we are not using a slave card or an auxiliary card, but an auxiliary cable. So we have developed that cable in order to connect to the PCI complex directly, the card. And every single connection is shared every 2 nodes. We do this with NDR 200 or with NDR. So one NDR connection can be shared, providing 200 gigabit per second to each compute node, or we can share the connection at NDR 200, providing 100 gigabit. So let's see more clearly how this is done. So this is well, this is a picture of the compute node SD650v3. That's the one that is being installed in Mare Nostrum 5, the data center you were visiting, or many of you were visiting yesterday in the afternoon. We will talk about this a little bit more. So this is a dense system, and even a large supercomputer like Mare Nostrum 5 is using this shared I/O approach. I mean, 100 gigabit per second per compute node. So to keep on comparing HDR, and this is simple math. I mean, I'm not discovering anything. HDR versus NDR. So with HDR, it was already a very good advantage that we could connect up to 80 HDR 100 endpoints to a single switch, with the subsequent savings in cost and cabling and things like that. So we can do this with the use of either splitter cables or the shared I/O card, just one single connection to the switch. Just a little bit difference in HDR is that sometimes with the shared I/O approach, you are having lower latency. Lower latency because the splitter cables introduce some latency. This is unavoidable in NDR because with NDR we always need to use splitter cables. Anyway, in any case, we can connect up to 80 compute nodes in a single switch, or for scalability, if you want to see, for example, 3-to-1 blocking factor between switches, between non-blocking islands of 60 nodes. It's a very nice blocking factor for many of the topologies that we are implementing, and still have 60 nodes under one single switch. But with NDR, this is even improved. Why? Because the higher radix, of course, we have more ports. As simple as that. We have more ports in each of the switches, so we can connect. With the use of splitter cables, we have these breakout cables of one connector to 4 NDR200 ports, and each of the NDR200 connectors can be also shared every 2 compute nodes. That meaning, for every single physical connector in the switch, we can have connected up to 8 endpoints at 100 gigabit. That's very interesting, and that's, first of all, saving money, saving cabling, and also saving complexity. Maybe, well, I will talk about this a little later, because I believe that I have the, yes, exactly. Okay, this is a little bit more in detail what you saw yesterday in the Mare Nostrum 5 data center at BSC. So it's a dual socket Sapphire Rapids compute node with 256 gigabytes of memory, some SSD, and the connection is shared every 2 nodes with NDR200. The good thing of it is that if you remember in the front line, in the first row of the data center, we saw a lot of cables that were connecting the core IB switches in the racks in the front line, the level 2 and level 3 switches, and we could save a lot of switches because of this feature. Because otherwise, we would need many more switches, and maybe we would have been pushed to use very monolithic and very expensive core switches of several thousand ports that at the end are made of leaves and spines and all that stuff. So we did it, but we did it manually, cabling 1U switches. That's the beauty of this approach for the shared I/O. Remember, one single connection every 8 nodes. So something to bear in mind, and still having 100 gigabit per second for every compute node, which is a very nice rate as well. Caveat: of course, this is only feasible for dense systems in dense format, because otherwise we would have to use long cables, external cables that are adding complexity, are adding cost, and not a lot of serviceability. And going dense in the very next future means going liquid cool. That's the caveat. And of course, I'm not talking today about liquid cooling. I already did in some past editions. I'm happy to discuss with you. We are very happy to explain the beauty of the direct liquid cooling. But this is it. Otherwise, with a dense system, air-cooled is also feasible, this approach. Just that you know that dense systems in the very next future with CPUs of 400 watt, 350 in the BSC, it's impossible to be cooled by air in a dense format. All right. So this was it so far. I hope I have not taken too much time. Do we have time for questions or?
Thank you so much.
Good morning.
Morning.
So I have two questions, actually. The first one is this, if you go back with your slides where you try to split between two sockets and trying to, yes, this direct socket. So now if I use socket 0, I won't have this problem, and I'm using the first, let's say, set of CPUs in the other node. I won't have that. I won't jump from one to another. Now with AMD, the link between the sockets is PCI Express.
Yes.
So does that has any impact? Does that we'll see? With Intel, it used to be with QPI, it used to be a big problem. Jumping from network, socket,
Agree.
1, and back to network. Would that be a problem with AMD? That's the first part. And the second is how much that would be, if there's an impact, how much that would be?
Honestly, I can't measure the impact, but it shouldn't be any problem. Just it takes some latency when I mean even if using not QPI but this hypertransport I mean the PCI based CPU interconnect, it's also introducing some latency. And well, it might yes, it might have a little impact. Yes, I don't think that the socket direct approach is currently being used for that, but we have leveraged it for the connection of two compute nodes to a single connection. So for us that's a good use. We used to do it in the past also when we ran out of PCI slots. Because we were featuring a machine with I don't know, with maybe a front end storage server with several SAS cards and whatever, and we ran out of PCI lanes, and we needed to provide a full bandwidth for something. So we used two PCI 8x8 slots for a single connection. That kind of tricks.
So we use it actually when we have like. The node is old generation and the card is the new generation of PCI Express, and we had to do the split to be able just to gain the maximum performance. So the first part. Second one has to do with the split of the one port, the 800 gigabit switch port that will split it to multiple. Is this available in the market? Because what I have a switch, the 400 gigabit, but the cards that they came with a split of 400. So I can go to the 400 gigabit on the host, while the switch port is 800. So is this available for every node to have like 1 to 8?
Okay, so this is a more detailed picture, but of the switch. Every connector is an 800 gigabit connector. And you need to use, but actually they are two ports. So the only way of using it is using splitters. So from each port, you provide two NDR connections. Yep. So for instance, if you have two NDR connections in your host, that's fine. You can connect it to a single port, or with the use of With the use of transceivers and optical connections, much more expensive, by the way, you can have also a kind of a redundant connection. You can have them connected to different switches with the use of this setup in the right side, on the right side. With the use of this setup, you can have it connected to different switches, and yes, or you can connect one single physical port to two NDR hosts differently, and you can also do it with a SharedIO and NDR 200, and have 8 connections per single physical port.
Okay.
I don't know if that answers the question.
Yeah, I'm just trying the calculation actually. My goal is just I wanted to go from one port, one switch, to 8 nodes.
Yes.
And exactly. And now I have the 1 to 2. Now maybe I need to get this 1 to 4, and then from the NDR I will just go as.
Yes.
Okay.
Exactly. The 1 to 4 is the possibility you have,
Yep.
and then once you get to the endpoint, to the adapter,
Yeah.
then you split it to the other node.
Okay.
That's it.
Thank you.
Yes.
Thank you.
More questions?
Yes, please.
Hello. Thank you for the presentation, Miguel. I've been quite surprised that such a novel machine like Mare Nostrum stays with 100 gigabyte network. So I understand that it's a decision based also on cost and complexity, but do you know if in this case BSC or any other center that buying such a machine is doing quite a benchmark to see the impact on the most current applications, HPC applications in the market, evaluating the impact and going to this technology that seems a little bit, more outdated?
Well, sorry, I didn't I didn't see you. No, I can't find you. Yes. Well, the impact is just the bandwidth. Performance-wise, only the bandwidth is impacted. So as long as your applications are bearing with 100 gigabit per second, that's fine, performance-wise. So there are some caveats. For instance, is that you have a single connection every 2 nodes. So if that connection fails, it's failing 2 nodes connection, of course. And we know that, and you need to know that and be aware of that. And also bearing in mind the size of your cluster. I mean, specifically for a large supercomputer, it's peanuts. I mean, 2 nodes not having a connection, okay, it's a hiccup, but this is it. And but regarding performance, just the bandwidth. That's it, because latency is not affected. Latency is not affected because every node is talking directly to the network.
Do you have any also micro benchmarks showing the latency between every single endpoint?
There are benchmarks, yes. I need to find them. Yes, not many, because this is emerging. I mean, it's been announced long ago, but it's now been implemented in the field. And so BSC is one of the first customers that are having NDR, and now it's generally available. And we need to do much more benchmarks, but yes, there are benchmarks that we can.
But if the latency is consistent everywhere, so it's a no-brainer. So it's
yes. Latency is not a problem, and in fact, latency is even better in the case of HDR. I mean, splitter cables are introducing some latency. The problem with NDR is that you need to use splitter cables by design. So but that's the impact. The SharedIO is not introducing, is even producing a very nice performance latency-wise, and also the possibility. I don't know if that's feasible to be implemented as is, but the possibility to talk between 2 nodes without going to the switch, which would be also an advantage. And they were looking also at the possibility of balancing the bandwidth between the 2 nodes. I mean, whenever a compute node is not using full 100 gigabit, the 200 gigabits are available for the other node. But that's something that we are not sure can be implemented right now. We have been talking to NVIDIA because that could be a very nice advantage as well.
So there's one more question over there.
Yeah, hello. Thank you very much for the presentation. You've actually partially answered my question, which was regarding the management of the pairs of nodes. So of course you've mentioned that if the cable breaks, or that's it. Now, my question was regarding the lack, if you cut the power to the node that holds the card, is there a form of hardware bypass that allows the secondary node that is downstream to still communicate with the switch, or do they both lose connectivity?
I'm afraid they both lose connectivity. If you lose power in one of them,
yeah,
I mean in the slave one, so to say, that's fine.
Yep.
Because the other one is keeping.
But not the primary.
Yes, yes, and that's a fact. It's an issue. Having said this, also bear in mind that this is intended to be implemented in dense systems that are sharing the power supplies. So usually, if you have a problem in one of them, a power problem in one of them, you're having in the two of them as well.
Which is a fair point, but you have more reasons to switch off a node than just a power problem. So the question was actually, you've shown a picture briefly that shows a high-density blade environment, which is the one you're deploying.
Yeah.
And you haven't, I guess from your answers, that the designers haven't planned a direct supply from the backplane to that specific chip to keep it active even if the node is down. Do you understand what I mean?
Yes, yes, and it's interesting. I will ask development and see what they are doing in this regard, because that
would solve
yes,
effectively the problem.
Yes, it's interesting. Yes, to have a kind of independent electrical connection to the backplane, exactly, or the midplane in this case. And yeah, well, thanks. Thanks. I didn't think about it, and I will talk to development and see what they are thinking about this.
Thank you very much.
Thanks to you.
Okay, we have time for just one more question.
So I'm thinking about collectives and all-to-all, you know, and in Infiniband usually, or on a network usually, we have this queue of QPs, or how they just, when we have multiple, they're talking to a single point, and that's becoming a single point of let's say, I don't want to say failure, but it will have like contingency in the network. And at a certain point, you go for deadlock.
Yeah.
So how, with having this 8 using single point, you know, I'm just wondering if that will be an issue if we do not really optimize very well this quality of service and have like using all the lanes in a network. Because I know Infiniband has up to 15 lanes could be used. Won't that be and interesting to avoid these kind when we are running collectives and all-to-all?
Yeah, yeah. Well, as of now, the bandwidth is cut it by half for every of the connections for each compute node. And this is, I mean, I mentioned the possibility of tuning the quality of service to balance bandwidth between two nodes and in a certain manner, but this is not yet implemented. As of now, it's just half the bandwidth, and to the system and to the operating system of the compute node, and also to the switch. This is an endpoint. This is it. So.
Yeah, because I mean, bandwidth I don't care in this case. So what I care about is just when you have a congestion on you know, from multiple points they are talking to a single point, which is like a portion of 8. That's where if I don't use all my lanes, I'm expecting problem. But anyway, I think we are out of time. Maybe we can take this offline. Yeah.
Yes. We need to give it a thought.
So thank you so much, Miguel.
Thanks to you.